In this video, we're going to talk about conservative vector fields and line integrals. I want to start by recalling a fact that we learned in our previous videos. Let F be a vector field. In our previous videos, we used F1 and F2 for the components, but from now on we're going to use M and N to describe the components of the vector field F. This is the notation that they use in the book. And then let C be a curve defined by R of t equals x of t, y of t, for t on the interval a to b. Then the line integral f dot dr is equal to the integral of m dx plus integral of n dx. But we can combine those together in one integral and write it as the line integral of m dx plus n dy over the curve C. Now in the previous video, we used this formula to help us calculate the work done by a force field on an object moving along the curve C. In the two examples that we looked at, we kept the force field the same, we kept the initial point and the end point the same, but the path that the object took differed, and that affected how much work was done by the force field. But there are certain situations where the path that the object takes does not matter. Let's take a look at this example. Suppose that a force field F given by y plus 2x and x moves an object from 0, 0 to 2, 4 in two different ways. In the first way, it moves it in a straight line, and the other along the parabola y equals x squared. Find the work done on the object in each way. Let's start with the first way where the object is moved along the straight line. So here, let's come up with a parameterization for this line. We know that the line goes through the point 0, 0, and it goes in the direction 2, 4. So the parameterization for this line would be r of t equals 2t, 4t, for t on the interval 0 to 1. The work done would be the line integral of f dot dr, which equals the integral of the x component of the force field, that's y plus 2x, dx, plus the integral of the y component of the force field, x dy. Okay, so let's write down what this is. This is the integral from 0 to 1. Y is 4t plus 2 times x, that's 2t, and then times x prime of t dt. X prime of t would be 2, and then dt, plus integral from 0 to 1 of x dy. So x is 2t, dy is y prime dt, so y prime is 4, and then I have dt. This simplifies as the integral from 0 to 1 of 16t dt plus the integral from 0 to 1 of 8t dt. Finding the antiderivative, I have 8t squared evaluated from 0 to 1 plus 4t squared evaluated from 0 to 1, giving me 12. So that's the amount of work done. Now let's calculate the amount of work done if the object moves along the parabola from 0, 0 to 2, 4. In this case, the parameterization would be r of t equals t squared for t's between 0 and 2. So my work done would look like integral over my curve of f dot dr, which is the integral of the x component of the force field, that's y plus 2x, dx plus integral of x dy. Okay. This equals the integral from 0 to 2. Y in this case is t squared. Then I have plus 2x, so that's plus 2t. dx is x prime of t dt. So x prime of t is 1, and then I have dt. Plus the integral from 0 to 2 of x, which is t, times dy. dy is replaced with y prime of t dt. So y prime of t is 2t, and then I have dt. These integrals simplify as integral from 0 to 2 of t squared plus 2t dt plus integral from 0 to 2 of 2t squared dt. Finding the antiderivative, I have 1/3 t cubed plus t squared evaluated from 0 to 2 plus 2/3 t cubed evaluated from 0 to 2. And again, when we plug those things in, we end up with 12. So in this example, I chose two different ways to move the object, and they both resulted in the same amount of work done. In fact, no matter what path I choose to take from 0, 0 to 2, 4, the work done will be the same. The reason for this is because f is a conservative vector field. So here's a theorem that I'll state, but I won't prove in this video. So the theorem says that the line integral f dot dr is independent of path if and only if f is conservative. So independent of path means that if you have a starting point and an end point, no matter what path you take, this line integral will always have the same value. And remember that we say that a vector field is conservative if there exists a real valued function whose gradient is equal to that vector field. Now the theorem then says that if I have a curve C whose initial point is x1, y1 and terminal point is x2, y2, then if f is a conservative vector field with potential function little f, then the line integral of f dot dr is equal to the potential function evaluated from x1, y1 to x2, y2, meaning it's f of x2, y2 minus f of x1, y1. And remember, the potential function here is the function whose gradient is that vector field big F. So this theorem here is called the fundamental theorem of line integrals. So previously, given a vector field f, we had a process for finding the potential function for f. If we were able to find the potential function using this process, then we would say that f is conservative. Otherwise, f was not conservative. But there's an easier way to check. So if f was the vector field with x component m and y component n, then f is a conservative vector field if and only if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. Now this rule applies when m, y, and nx are continuous functions, but that's going to be true in most situations. So now let's look at some examples. So in this example, we have the vector field f equals y squared plus 2e to the 2y, and then 2xy plus 4xe to the 2y. Suppose that C is a curve from the point 1, 0 to 2, 1. We want to calculate the line integral of f dot dr over the curve C. If I want to use the fundamental theorem of line integrals, I would first need to check if the vector field f is conservative. Let's check by using the test that I just mentioned. So remember that m is the x component of the vector field, and n is the y component of the vector field. So the partial derivative of m with respect to y is 2y plus 4e to the 2y. Then we want to check the partial derivative of n with respect to x. That's going to be 2y again plus 4e to the 2y. So we see here that my is equal to nx, which allows me to conclude that f is a conservative vector field. So next, if I want to use the fundamental theorem of line integrals, I would need to find a potential function for f. So our potential function f is the integral of the x component of the vector field with respect to x. The antiderivative here would be xy squared plus 2xe to the 2y. And then I have a constant. But this constant could involve y's because when we're integrating with respect to x, we're treating y's as constants. In our next step, we want to take the partial derivative of f with respect to y. That's going to give me 2xy plus 4xe to the 2y, and then plus r prime of y. So next, we'll set this equal to the y component of the vector field and try to solve for r prime. So subtracting things from both sides, we have that r prime of y is equal to 0. When we integrate r prime of y, we get r of y equals some constant c. So our potential function for the vector field f is xy squared plus 2xe to the 2y plus c. Now let's apply the fundamental theorem of line integrals. We have that the line integral of f dot dr is the potential function evaluated from the initial point 1, 0 to the terminal point 2, 1. So I'm going to evaluate my potential function xy squared plus 2x e to the 2y plus c from 1, 0 to 2, 1. So plugging in 2, 1, I have 2 times 1 squared plus 2 times 2 e to the 2 times 1 plus c. And then I'm going to take this and subtract, plug in the point 1, 0. I have 1 times 0 squared plus 2 times 1 e to the 2 times 0 plus c. So that's going to be 2 plus 4e squared plus c minus 2 minus c, which simplifies to just 4e squared. As you can see, if f is a conservative vector field, calculating the integral of f dot dr becomes much easier. In this example, let f be the vector field 2x plus y, x plus z squared, and 2yz minus 1. And let c be a curve from the origin 0, 0, 0 to the point 1, 1, 1. And we're asked to calculate the line integral f dot dr. So here notice that our vector field f is a three-dimensional vector field, and we're working in three-dimensional space. Although we've only been looking at things in 2 dimensions, things generalize to 3 dimensions as well. For example, this line integral breaks apart into the line integral of the x component of f, the 2x plus y, dx, plus the line integral of the y component of f, the x plus z squared, dy, plus the line integral of the z component 2yz minus 1, dz. So if we had a parameterization for our curve, this would be one approach for calculating this line integral. The fundamental theorem of line integrals also holds in 3 dimensions. If we know that f is a conservative vector field and we can find the potential function for f, then we can evaluate the line integral f dot dr by evaluating the potential function at the endpoints. But unlike the 2-dimensional case, right now there's not a quick way to check whether f is conservative. So we'll just have to try to find the potential function. So first I'm going to integrate the x component of the vector field with respect to x and set that equal to f. When I integrate that, I get x squared plus xy plus a constant. But since y's and z's are constants when I'm integrating with respect to x, my constant here at the end could involve y's and z's. Next, I'm going to take the partial derivative of f with respect to y and make sure it matches the second component of f. So the partial derivative of f with respect to y would be x plus ry of yz. I'm going to set this equal to the y component of f and then try to solve for ry of yz. So subtracting x from both sides, I get that ry of yz is equal to z squared. I'm going to take this equation and integrate by y on both sides to get integral of ry of yz dy equals integral of z squared dy. On the left it gives me r of yz, and on the right we get yz squared plus some constant. This constant I'm going to call q, but because r is a function of y and z and I'm integrating with respect to y, I'm treating z as a constant. So this constant at the end here could involve z's. So now that I know r of yz, I have a better idea of what f is. F I can write as x squared plus xy plus now yz squared plus q of z. Now if f is a potential function for f, then the gradient of f would equal big F. So I need to make sure that the partial derivative of f with respect to z will match the z component of the vector field. Now if I take the partial derivative of f with respect to z, I get 2yz plus q prime of z. I'm going to set this equal to the z component of the vector field to try to find q. So set this equal to 2yz minus 1. Subtract the 2yz from both sides, I get q prime of z equals negative 1. Now integrate both sides with respect to z, and I get that q of z equals negative z plus some constant c. Now this time the constant is just a constant because q was a function of one variable. So now we have f. F is x squared plus xy plus yz squared minus z plus c. And you can check that this is indeed a potential function for the vector field f. Now that we have the potential function, we can evaluate the line integral of f dot dr using the fundamental theorem of line integrals. So this is the potential function f evaluated at the endpoints 0, 0, 0 and 1, 1, 1, which is f of 1, 1, 1 minus f of 0, 0, 0, which is 1 squared plus 1 times 1 plus 1 times 1 squared minus 1 plus c minus 0 squared plus 0 times 0 plus 0 times 0 squared minus 0 plus c, which is just 2. So this is how you would evaluate the line integral of f dot dr when you have a three-dimensional vector field and you know it's conservative. One last remark is this. If f is a conservative vector field, then the line integral f dot dr is equal to 0 for any closed curve C. And a closed curve is just a curve where the initial point is the same as its terminal point. So you can see that this fact is true using the fundamental theorem of line integrals. Because if the vector field f is conservative, then the line integral of f dot dr is just a potential function evaluated at the endpoints. And for a closed curve, the endpoints are the same. Therefore, when you plug them into the potential function and then subtract, you get 0. So that's it for this video. In the next video, we'll look more into closed curves and how we evaluate the line integral of f dot dr when the vector field f is not conservative.